Okay, good afternoon to all.
Good afternoon, sir.
Can you see the screen? PPT?
Yes, sir.
Okay,
Good
Yes, sir.
afternoon, sir.
good afternoon. Good afternoon. So we have now 82. We can wait for 1 or 2 minutes more. So now if you any problem in any links or what LabTude or everything is going fine now as for this subject UVC 001.
So fine, sir.
Okay, good. Okay, so this is our third lecture, and in the last lecture I discussed few aspects, administrative aspects like how to access LMS, how to access the website, and what will be the evaluation strategy, and what are different components like LabTude, lecture, and then I moved to this course learning objective that was taken from your syllabus, and our syllabus is defined broken into 5 different topics. So I have already discussed what are the topics in each what are the components of each of these topics, and I have already shared the PDF of book textbook, that is Robert R.L. Boylston to the GRs. So if you have not gotten till now, please contact them. Okay, and this thing, all the things I have already discussed, that what we are going to do, what we are going to do in the analog part, what we are going to do in the digital part, and I recapped basic Noodles theorem that are KCL, KVL, and then this is our first unit, that is PN junction diode. So in this we have to study ideal diode, VI diode, VI characteristic, and its small signal model, its switching characteristics, and Zener diode. So uh, before that, I started with this thing, that semiconductor materials. So from the electronics point of view, uh, uh, we categorize material into 3 different categories. First is conductor. Second one are insulators, and third one is, that is, semiconductor. Okay, so now for electronics, we have to study the semiconductor majorly, and the material that is ruling the semiconductors industry at present is silicon. Okay, earlier it was germanium, and for high speed devices, for very high speed devices, this is the area of research, gallium arsenide. This material is for electronic devices, and I told you that gallium nitride is for optoelectronic devices like white and blue LEDs. So uh, now we can categorize. How do we categorize the material? So we use basically this parameter, uh, energy levels, energy band diagram. So insulator, for insulator, this gap, energy gap is greater than 5 eV. We have valence band. So this vertical axis, this is representing the energy level, increasing level of energy. So this represents valence band, very low amount of energy. This is a high amount of energy. This is representing a high amount of energy, and we named it as conduction band. And in between, we have a forbidden gap. So electron either can lie in valence band or can exist in conduction band. In between, there is no place of electron. So there is a very complex device theory for this. Yes, Mayank.
Sir, some students are waiting in the waiting lobby.
Waiting. I have disabled then too. Okay, let me check. Okay, so there is no waiting room showing.
So the students may have joined the wrong link, as it's on the timetable. It's a wrong link.
Okay. So can you help them?
Yes, I'll resend them the link.
I have disabled the waiting room. There is no problem from this end.
Okay, sir. Thank you.
Okay. Okay, so is this screen is still visible? Energy level screen?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay, so again, I have to select pointer. Okay, for conductor, it overlaps. Conduction band and valence band overlaps. Okay, so there is overlapping. That's why just by applying small amount of voltage or electric field, this current starts flowing across them. It is having a very lower amount of resistance level. And semiconductor, this is intermediate value, neither this much greater nor its overlap. So it is like 0.67 volt for germanium, 1.1 for silicon, and 1.43 for gallium arsenide. So this is the material that we will be discussing more and more. Silicon 1.1 electron volt. Okay, so this difference is 1.1 eV for silicon. Okay, and you all know that silicon is a fourth group element. It is having 4 electron in its outermost most shell, and germanium is also a fourth group element having 4 electron in its outermost shell. So silicon cannot form ionic bond as such. It to complete its octet, it have to form covalent bond. So this is the two-dimensional structure of silicon crystal. Okay, silicon crystal. That crystal is used for fabricating IC. So there is a specific technique, a very specific and technique using which this crystal is formed. Okay, so this is a two-dimensional view. So you can see that silicon are arranged in a regular pattern. So considering this silicon, the center one, it is having 4 valence electron. Okay, and to complete its octet, it is sharing 4 electrons from the neighborby electron. Okay, so this one is being shared by this leftmost silicon. This is shared by the rightmost, then from the top one, and then from bottom one. So this is how this silicon is completing its octet, having 8 electrons. Okay, and is a this pattern is repetitive. Okay, no matter whichever silicon atom you take, this will be the case. It is sharing 4 electrons from the neighbor ones. Okay, so this is a periodic structure of silicon crystal, and this is called intrinsic. This is called intrinsic. So the term intrinsic is applied to any semiconductor material that has been carefully refined to reduce the number of impurities to very low level, essentially as pure as can be made available through modern technology. Okay, so this pure material, having pure material is very, very important. Even the impurity of 0.0001% can hamper the functioning of the device. Okay, so very pure material is required, but nothing is ideal. We cannot achieve 100% purity. So almost very close to 99.99999 kind of percent, that much amount of material we try to achieve, and that kind of material is called intrinsic material. Okay, and you can see that in this material, number of free electron is equal to number of holes. So we will come to this, what is meant by home and what is meant by free electron. Okay, this equation is written over there, so we will see this in more detail. Okay, so this is the energy band diagram, and this is the 2D structure of any atom. You can consider it like for silicon atom. Let it be for silicon atom. Okay, so these are correlated. Okay, these are correlated. Okay, so this valence band, what is this representing? This is representing that electron is in bond. You know that each and every particle in the universe tries to be in the lower energy state. We call it as equilibrium. Okay, lower energy state. This is a higher energy, and yes, Ayush.
Sir, I was not able to join because like it was coming waiting. So can you explain like what you have explained before?
Oh, this is again the issue. This is being recorded. Okay, let me check if it is recorded or not. Yeah, this is being recorded. Okay. अब मैं again and again repeat करूंगा तो बाकी 100 लोग बोर हो जाएंगे.
Yes.
और मैंने कुछ ऐसे खास नहीं किया, सिंपल. दिस इज द 2D स्ट्रक्चर ऑफ सिलिकॉन मॉडल, +2 में देखा होगा, और ये उसका एनर्जी बैंड डायग्राम है. तो दोनों में क्या कोरिलेशन है वो मैं समझा रहा था. मैं एक बार स्लाइड गो थ्रू कर देता. ये आपने देखा है, ये तो लास्ट क्लास में भी यहाँ तक किया था, बस मैंने ये समझाया था और यहाँ पे मैं आया था. दैट्स इट.
ठीक है.
So these two structures are now correlated. Okay, so what I was saying that every particle wants to be in the lower energy state, that is called equilibrium state. Okay, so equilibrium state for electron, a low energy state for electron, is in the form of bond. If the electron is in bond, this means that it has lost all of its energy. Now it is in its equilibrium state. Okay, so this low level of energy is represented by this valence band. Okay, so if I say that the electron is in valence band, okay, so this means that this is in bond. Okay, maybe covalent or ionic, whatever. Okay, now suppose by providing external source of energy, let's say that 1.1 eV for silicon, 1.1 eV is required to break one bond. Okay, or energy greater than 1.1 eV. So let's say that I have provided some external radiation on this, and radiation means photons. Photons are kind of particles. Okay, so I have provided photons, and the energy was greater than 1.1 eV, and let's say it falls on this bond, and this electron now will absorb this energy. Okay, so now it will have some energy, and it can now move out of the bond, and then it will start moving randomly, Brownian motion. Electrons move like the zigzag motion. We say that it is a Brownian motion. Okay, so now it is having some kinetic energy. So comparatively, its energy has been increased compared to electrons in bond. Comparatively, its energy has been increased. So now it is having some higher amount of energy. So we say that it is now in conduction band. So this is the difference. It is not like this is a kind of a building, this is first floor, this is something intermediate floor, this is top floor. No, these two are correlated. And this is also, it is a very, this is D versus energy. This D is the distance of electron from the center of nucleus. So this diagram is very complex. This, what you are seeing is just a single point of this. Yes, Mayank?
एक्सक्यूज मी सर, सर ये जो ईजी है इसमें
हम्म,
सर ये बॉन्ड एनर्जी होगी SI
हाँ, बॉन्ड एनर्जी सिलिकॉन के
Okay,
सिलिकॉन के लिए 1.1 होगी, ये जर्मेनियम के लिए 0.2. Okay, so h mu, this h mu, mu is the frequency, so h is the Planck's constant, so h into mu is the energy of the photon. Okay, so yes, so these two are correlated. Okay, ये सब्जेक्ट से रिलेटेड नहीं है, मैं जस्ट अभी रिकैप ही कर रहा हूँ. वैसे तो इसका वीडियो अवेलेबल है, आप उसमें प्री रिक्विजिट में दे रखा है, बट देन टू जस्ट ब्रीफ, इसलिए मैं ज्यादा ब्रीफ में नहीं जा रहा. उसका वीडियो अवेलेबल है, एंड बिलीविंग दैट कुछ आपने पढ़ा होगा +2 में. ठीक है, हमें स्टार्ट एक्चुअली पीएन जंक्शन से करना है, बट स्टिल आई एम रिकैपिंग सर्टेन थिंग्स. ओके, सो नाउ what if external radiation is not there? So does it mean that there will be no free electrons? Okay, you know that current is dq by dt, rate of flow of charges. Rate of flow of charges gives you current, and if this charges should be free in state. बॉन्ड में होंगे तो कैसे फ्री होंगे? फ्री तो हो ही नहीं सकते. बॉन्ड में तो वो फंसे हुए हैं, है ना. बॉन्ड का वर्ड का मतलब ही यही होता है. सो दिस चार्ज शुड बी इन फ्री स्टेट, तो बॉन्ड के बाहर आना पड़ेगा. सो I is dq by dt. So does it means that in intrinsic semiconductor, this is the ideal state of intrinsic semiconductor, every electron is in bond. Okay, there is no free electron. So it means that there is no current possible. This intrinsic semiconductor cannot be used for commercial purpose. Okay, but this is not the case. We have few number of electrons, few number of free electrons that are not in bond, and we have holes. Again saying that holes क्या होता है वो फिर हम देखेंगे एक बार वापस दोबारा डिटेल में. Okay, and why this is the case? Ideally it should be in the bonded state. Why this is the case? Because of thermal generation. We have like 27-degree 30-degree room temperature like this. Okay, so this temperature amounts to heat, and heat is also a form of energy. Okay, so in absence of radiation, no problem, we have thermal generation. So the electron generating because of this thermal energy, this thermal heat, that process is known as thermal generation. Okay, so how the electron can be in free state because of thermal energy? Okay, because it is written over there that because of thermal energy, the atoms in the crystal, these are the atoms. Okay, so because of the thermal energy, the atoms in the crystal are constantly vibrating. Okay, and that corresponds to bond between Si atoms being periodically deformed. Okay, you can imagine like you have two points where you have tied thread, and now you are moving that two ends. Okay, if you move up, and if you fix one end and if you move the second end up and down, so you can you can imagine that there will be a kind of sine wave generation in that room. Okay, so if the atoms in the crystal are vibrating, so it is obvious that the bond between them will also vibrate. And if this vibration is very large, it can result in a rupture bond. Okay, and hence electron and hole pair can generate. So there is a fixed amount of electron and holes present in an intrinsic semiconductor because of the thermal generation, and its value is given here. For silicon, we have 1.5 into 10 to the power 10. It is written that per cubic centimeter. So if you take a cube like this of dimension 1, 1 cross 1 cross 1. So this is a cube of 1 cross 1 cross 1, and this is made up of silicon. So number of free electrons in this silicon will be 1.5 into 10 to the power 10. Okay, in germanium it will be 2.5 into 10 to the power 30, and in gallium arsenide it will be 1.7 into 10 to the power 10 to the power plus 6. So this will be the case. You have silicon atom periodically arranged, and because of thermal generation, let's say that this bond is broken. So now this electron is in free state. So we will say that this electron now corresponds to valence band. This electron is in valence band. This electron is still in uh, this is in conduction band, and this electron is still in its valence band. And how many number of such free electrons will be there in 1 cubic centimeter? It is given that 1.5 into 10 to the power 10. Okay, but that too is a very small amount. That much amount of electron are not sufficient to use this intrinsic silicon crystal for some meaningful purpose. Okay, so in that case, what we have to do, we have to do doping. But before doping, we will see this electron flow versus hole flow. What is the meaning of this electron and hole? Okay, so if a valence electrons, now I will discuss that how what is meant by hole, how it is generated, and how it contributes to the flow of current. Okay, so now if a valence electrons acquires sufficient kinetic energy to break its covalent bond, okay, so and fill the voids created by hole, then what happens? A vacancy or hole will be created. So let's say this is the case, and suppose the electron at this point is missing. Okay, let's say the electron is here. So there is a hole created. Okay, so a vacancy or hole, it is created in the covalent bond. Okay, this has just released the electron. So this electron in its free state, and a vacancy is created. So this is called hole. Okay, so it is very easily understandable that this electron is contributing flow of current, because this is in free state. But the question is that how we can say that hole also contributes in current. Okay, so you can see that the electron nearby, for this, consider this electron in the nearby silicon atom. So suppose this this electron is striken by some external photon of let's say 1.1 eV. Now this energy is sufficient to release this electron out of the bond. Okay, so now because of this electron will get out of the bond. Okay, so this is the case. Now this electron has been out of the bond. So a hole at this point will be created. Okay, and now this electron will move in random motion, and it will not sustain the kinetic energy which it has gained at this point. So eventually the kinetic energy will started decreasing, and at a point the energy will be so less that this electron will be easily attracted by the positive charge that are protons. Let now you imagine that this electron is having a very less amount of kinetic energy, so this get attracted by the positive proton charges present in this boron. Okay, so now this electron will be captured by this boron. Okay, so now see the case. Now electron exists here, and hole is created at this point. Okay, now imagine that now this electron gets free by some external excitation, and it will start moving, and at some point it sits here. So there will be hole at this point. And after that, let's say that this electron gets excited. After moving some distance, it sits here. So there will be a hole at this point. So eventually electrons are moving like this, but we will feel electrons are moving like this in anti-clockwise direction. Electrons are moving in anti-clockwise direction, but you will get a feel that holes are moving in clockwise direction. Okay, the best analogy for this is, suppose you have a bottle and it is filled with water and there is a bubble. Okay, so this bubble is what? Absence of water. No material is present in them. Quantity of water is so large that we feel that this is the particle and this is nothing. So whenever you tilt that bottle up and down, So water is moving accordingly, but you will feel that these bubbles are moving in upward and downward direction. Okay, so this is the scenario with holes. Actually, holes are not moving; electrons are moving. Okay, and we will feel that holes are moving in opposite direction. So this is the difference. This is the difference. We have free electron and we have holes. So this contributes to the flow of current. This is free in state, and this hole, actually electron is moving. It is jumping from one place to this. This is the vacancy, so this is jumping from this to this. Okay, then here a vacancy is created. Now this is jumping from this to this. This is jumping from this to this. So because of this also, current will flow. So to distinguish between these two phenomena, one is current because of free electron, and second is current because of this jumping thing. Electron is jumping from one vacancy to another. So to distinguish between these two phenomena, we have termed a new particle that is known as holes. Okay, अगर इसको भी इलेक्ट्रॉन बोल देंगे तो confusion का chance रहेगा. This is also free electron, this is bonded electron. So to avoid confusion, we called it as holes. This is the concept. Okay, तो ये दोनों अलग अलग चीज है. हो इलेक्ट्रॉन की वजह से ही रहा है, बट एक इलेक्ट्रॉन बिल्कुल फ्री स्टेट में है, क्रिस्टल के बीच में बहुत फ्रीक्वेंटली फ्रीली मूव कर रहा है. दूसरा वाला एक वैकेंसी से दूसरी वैकेंसी पे जंप हो रहा है. हाँ जी, पूछ लो कौन किसको डाउट है. Please unmute yourself and you can ask the question. Hello. This PPT is not available on the LMS. I will provide it to you. Okay. Yes. Yes, सीधा unmute करके आप पूछ लीजिए. Any more doubt?
नो सर,
Okay. किसी ने hand raise किया था तो पता नहीं.
वो सर मेरे से हो गया था गलती से.
Okay, fine. Okay, so okay, so this thing I was saying, that this electron is completely in free state, and this is the hole. So this electron will jump from this to this. Now there will be hole at this point, so this will jump from this to this. So दो अलग अलग phenomena है जिसकी वजह से current flow हो रहा है. Okay, so that's why we say that I is function of free electron and holes. Okay, and which particle will move faster? Movement of which particle will be faster? Electron or holes?
Electrons.
इलेक्ट्रॉन.
Free electrons. Obviously, it is in free state. Okay, this is in bonded state. पहले energy आएगा, टूटेगा, फिर जाएगा. So this is a slow process. First, it has to absorb energy, then it will then it will break. Then it have to find some vacancy, other vacancy. Then it will reside over there. Then it will lose energy. That is a slow process. This is free. Just to provide a proper appropriate amount of voltage or electric field, it will start flowing in that direction, and you will get current in opposite direction. Okay. So ये एक अगर हम देखें ऐसे, so free electron exists in conduction band, and this exists in valence band. So this was the case in this PPT. External radiation falls on this bond, the electron get excited, electron move to conduction band, and holes remain in the valence band. So this is the case. Okay. And it is obvious that this electron is having a higher amount of energy. So just you have to provide a little bit of external energy. This is having a lower amount of energy. So more amount of external energy has to be provided to make it flow. Okay, so this is the intrinsic semiconductor. This is already discussed. Okay, so I was saying that now this value of, okay, so that the number of free electrons, now that statement makes sense. Number of free electron in this, number of free electron, that will be equal to number of holes. Electron के free होने से ही तो holes create हुआ है, so obviously number of free electron will be equal to number of holes. And this says that this is the quantity of free electrons, 1.5 into 10 to the power 10. So obviously number of holes will be the same, 1.5 into 10 to the power 10 in a cubic centimeter of silicon crystal. Okay, so number of free electrons will be equal to number of holes, and that will be equal to 1.5 into 10 to the power 10 for silicon. So basically, if you take this cubic crystal, so it should be electrically neutral. Okay, so it is electrically neutral. So one more thing, this this electron, suppose this electron flows in this direction, and then there will be vacancy, this will be in this direction. So electron is, suppose if electron is this jumping in clockwise direction, so we will feel like holes is jumping in anti-clockwise direction. Okay, so we also know that if electrons flow in this direction, current is in the opposite direction. If this is the direction of electron, current is in its reverse direction. So that's for the same reason, for that region we denote H as plus. So now holes is also flowing in the same direction, in the reverse direction from right to left, and current, direction of current is similar to the direction of holes. So that's why we termed it as, we consider it as a positive charge particle, and we denote it as H plus, and this is denoted as E minus. Okay, so now this quantity 1.5, the number of free electrons is very, very less. We cannot have any meaningful amount of current from this much this electron. So what we have to do, we have to increase the number of electron. We have to increase the number of electrons or number of holes, and for that we do doping. This is the technique by which we can either increase the number of electrons or we can increase the number of holes. Both contribute to the current independently. So either the increase this or this, both cannot be increased simultaneously. Okay, you will see why. So doping is nothing but it is addition of impurity to increasing electron. Okay, so the electrical characteristics of silicon and germanium are improved by adding material, and that material are called impurities. So basically we are adding impurities deliberately, we are adding. Okay, in the first step we produce very pure silicon crystal atom, so this is necessary, you cannot skip this step. So production of pure silicon crystal is mandatory. After that you deliberately add impurities, so that deliberately adding of impurities is termed as doping. अगर इसमें कोई impurity रह जाएगा, then it is not going to help us. That is called doping. And the intrinsic semiconductors are doped, and we can have two different kind of semiconductor. So the base material is intrinsic, and you can add impurities to this intrinsic semiconductor, and you can create it to either N-type semiconductor material or P-type semiconductor material. So N-type material contain an excess of conduction band electrons. So N-type, as the name is reflecting that we have more number of electrons in N-type semiconductor, and in a P-type material it will have excess of valence band holes. So this is the main difference. Okay, and first we will discuss the creation of N-type material. Okay, so N-type material contains an excess of conduction band electrons, and it is created by introducing impurity element that have 5 valence electrons. So silicon is having 4 valence electron, or then if you want to have free electrons, So you should replace the silicon with atoms which are having electrons greater than 4. Okay, so generally what we do, we add the elements that belongs to fifth group, pentavalent impurity. So element of fifth group have 5 valence electron, pentavalent materials like antimony, arsenic, and phosphorus. Okay, so 4 covalent bonds are still present. However, an additional fifth electron due to the impurity atom, which is unassociated with any particular covalent bond. And this fifth electron, this remaining electron, is loosely bounded to its parent atom. Let's say that antimony is being introduced. So this electron is relatively free to move within the newly formed n-type material. And since the inserted impurity atom has donated a relatively free electron to the structure, this diffused impurity with 5 valence electron are called donor atom. So these are two terms, donor atom and this will be element of fifth group, okay, having 5 valence electron. So this is the pictorial representation of n-type doping. So this is antimony. So you have deliberately added antimony. We have 2 or more process like diffusion or ion implantation, that kind of process we have for doping. So imagine that silicon was present there, and due to this doping process, this silicon is now replaced by this antimony, and it is having 5 valence electrons. Okay, so the 4 electrons will be shared by the nearby silicon atom. So 1, 2, 3, 4. These 4 electrons are shared by the nearby silicon atoms. But what about this fifth one? This is still bounded to this antimony atom. Okay, and it cannot be shared by any other atom. Okay, because the silicon atom needs only 4 electrons. That's it. So this is loosely bound. Neither it is completely free nor it is in bonded form. Okay, so now again coming to this energy band diagram. So this valence band, that represents electron that are in the bond, lowest amount of energy. Free electron, if the electron is entirely free, then we say that this electron is in conduction band, highest amount of energy. What about this energy level of this this loosely bounded electron? So it is neither in bond, so we cannot say that it is in valence band. It is nor it is in free state, complete free state. So nor we can say that it is in conduction band. So its energy level will be somewhat in between. Okay, in this region. So now since this is a loosely bounded electron, okay, so just by providing a very small amount of energy, you can excite this electron into a free state. So the energy level that corresponds to this loosely bounded electron will be somewhat close to conduction band. This will be around like 0.2 or 0.3 or 0.02 eV. This much, very small difference between that. Okay, so this is the energy level that belongs to this electron, and now by supplying just a small amount of energy, we can excite this electron. So let's say that 0.2 eV of energy is given from the external source. So this electron gets free. Okay, now I can say that this electron is now in conduction band. So this is the concept of creating a n-type semiconductor. Okay, make this difference very less. So instead of giving 1.1 EV, I have to just supply 0.2 EV, and this is easier. जितना कम एनर्जी मैं यूज करूंगा उतना मेरे लिए अच्छा है, एक्सटर्नल सोर्स के लिए अच्छा है, इतना इजीली मैं जनरेट कर सकता हूँ. Okay, so you can see that by this process, is there any extra hole created? No extra hole is created. Okay, so you have just one free electron. And what is the doping figure? Suppose if you have 1 million silicon atom, 1 million means 10 lakh. So the proportion of this antimony is 1. You add only 1 fifth group element for 10 lakh silicon atom. This much amount quantity is sufficient to produce a N-type semiconductor that can be used for commercial purpose. Okay, so I'm just giving you some extra knowledge. So maybe you can use it somewhere in objective type or somewhere else. So now you can see that number of free electrons will be obviously greater than number of holes. Okay, so first free electrons will be due to this, due to antimony atom. Okay, you can make it free just by providing 0.2 eV of energy. Second, free electron will be due to thermal generation also. Okay, you cannot ignore that. This is a natural process, thermal generation. For this, energy, minimum energy is 1.1 eV is required. Okay, so you have free electron now from two sources, one from the impurities and second from the this thermal generation. That is a natural process. So because of this thermal generation, some amount of holes will also be created. Okay, but still you have additional electron because of this antimony atom. So you can say that number of free electrons will be always greater than number of holes. This is the case. And this antimony atom, this is known as donor atom. This is donating its free electron. Okay, so once it donated this electron, so there will be one proton more. Okay, at this point, number of proton is equal to number of electron. But when this free electron, when this electron gets free, it will have one extra proton and it will have plus charge. Okay, so please remember this. This is somewhat confusing. This concept is very important for understanding the depletion layer, how depletion layer is created in PN junction diode. Okay, so in N-type semiconductor, the donor atom is having positive charge after losing electron. Please do remember this. Okay, and talking about the net charge will be still 0 because number of protons in the system, number of protons will be number of electrons. So although you are having free electrons greater than number of holes, but that free electrons is balanced by number of protons, so your crystal will be still electrically neutral. And
Sir, excuse me, sir.
yes, Akshat.
Can you repeat that proton thing?
सर पॉजिटिव चार्ज कैसे होगा उस पे दोबारा बताना एक बार.
Yes, sir.
ये आपका एंटीमनी है, इसके इस वैलेंस बैंड में 5 इलेक्ट्रॉन होते हैं, 1 2
Yes,
3
sir.
4 5. ओके, तो इसमें जो अभी केस है टोटल नंबर ऑफ प्रोटॉन्स, इसका एटॉमिक नंबर मुझे याद नहीं है, लेट्स से दैट इट इज p. so total number of protons will be equal to total number of electrons, तभी इलेक्ट्रिकली न्यूट्रल है. ठीक है, अब क्या हुआ, एक्सटर्नल सोर्स, ये 4 तो बॉन्ड बन गए, सिलिकॉन से बॉन्ड बना लिया इन्होंने, ये लूजली बाउंडेड है. ठीक है, still it is associated with it, still it is in valence band of this antimony, but it is not shared by any other silicon atom, so means it is very loosely bounded. अब मान लीजिए कि कोई एनर्जी सोर्स आता है और ये बॉन्ड टूट जाता है, ये बॉन्ड एंटीमनी से,
समझ आ गया.
हाँ, ये
समझ आ
बॉन्ड
गया, अब आ गया.
ओके, ठीक है, अंडरस्टूड.
Yes,
ये
sir.
नेट
Yes.
चार्ज वाला समझाना, नेट चार्ज.
हाँ,
zero
मैं उसी पे आ रहा हूँ. सो देखो, अभी वो मैं वही चीज कंटिन्यू करता हूँ कि मान लो ये आता है और ये इससे, ये वाला जो इसके वैलेंस बैंड में था वो इसके वैलेंस बैंड से निकल के बाहर आ जाता है, क्रिस्टल में आ जाता है.
Yes.
ठीक है, अब इस एंटीमनी के रिस्पेक्ट में बात करते हैं हम. इस एंटीमनी पे नेट चार्ज क्या होगा, पहले P was equal to E, now E is E minus 1, it has lost its 1 electron.
Yes, sir.
So now P is 1 greater than E. P is greater than E by how much amount? Just by 1. So इस एंटीमनी पे क्या आ जाएगा, पॉजिटिव चार्ज आ जाएगा इस एंटीमनी पे. ओके, एक इलेक्ट्रॉन इसने लूज कर दिया तो ऑब्वियसली इस पे एक इलेक्ट्रॉन कम हो गया. पहले ये इलेक्ट्रिकली न्यूट्रल, पहले सपोज 32 इलेक्ट्रॉन्स थे, 32 प्रोटॉन्स थे, और मान लो 5 वैलेंस में थे, 5 सबसे आउटर मोस्ट शेल में थे. उसके बाद क्या हुआ, आउटर मोस्ट शेल से एक इलेक्ट्रॉन चले गया, तो अब आउटर मोस्ट शेल में 4 रह गए. अब इसके पास टोटल नंबर ऑफ इलेक्ट्रॉन 31 है और प्रोटॉन स्टिल 32 है. तो दोनों का डिफरेंस कितना हुआ 1, सो ऑब्वियसली इस पे एक पॉजिटिव चार्ज आ जाएगा। अच्छा अब मैं ये जो मैं इलेक्ट्रिकल इसकी जो मैं
एक्सक्यूज मी सर।
यस
सर बट ओवरऑल चार्ज तो न्यूट्रल ही रहेगा ना उसपे।
तो वही तो ये लिखा है नेट चार्ज,
यस सर।
दैट्स व्हाट इट मीन, नेट चार्ज इज स्टिल 0। नंबर ऑफ प्रोटॉन, सारे जितने भी एटम्स है आपके क्रिस्टल में, जितने भी सिलिकॉन एटम्स और जितने भी एंटीमनी एटम्स है, उसके टोटल नंबर ऑफ प्रोटॉन्स और टोटल नंबर ऑफ इलेक्ट्रॉन, चाहे वो बॉन्डेड स्टेट में हो या फ्री स्टेट में हो, दैट विल बी ऑलवेज इक्वल। ठीक है हमें
सर
हाँ
पर हॉल्स भी तो है जिसके लाइक हॉल्स के हॉल्स पे पॉजिटिव चार्ज होता है, तो वो
होल्स
भी न्यूट्रल
इलेक्ट्रॉन,
रहेगा।
वो होल्स का इलेक्ट्रॉन ही तो फ्री स्टेट में आ रहा है।
ठीक है।
वही तो मैंने समझाया था कि होल्स नहीं है वो है इलेक्ट्रॉन ही, बट वो फिनोमेना थोड़ा सा डिफरेंट है, इसलिए हमने उसको नाम होल्स दे दिया।
ओके
होल्स इज अ स्यूडो पार्टिकल। ओके होल्स इसकी मैंने बताया ना, होल्स इसकी वजह से आएंगे, ये तो फ्री इलेक्ट्रॉन है। अब ये जो सिलिकॉन का ये जो बॉन्डेड इलेक्ट्रॉन है, ठीक है, इमेजिन दिस, अब इस पे ध्यान देना, ये सिलिकॉन सिलिकॉन के बीच में बॉन्डेड है, तो ये तो इसको भूल जाओ, अब इसको ध्यान रखो। अब ये फ्री स्टेट में आ गया, तो यहाँ पे क्या क्रिएट हो गया, एक होल। ठीक है, यहाँ पे क्रिएट हो गया इलेक्ट्रॉन, तो अगेन ये दोनों एक दूसरे को बैलेंस करेंगे। तो यहाँ पे इसलिए मैंने दो अलग अलग चीज लिखी थी, फ्री इलेक्ट्रॉन बिकॉज ऑफ द दिस डोनर एटम एंड फ्री इलेक्ट्रॉन्स बिकॉज ऑफ थर्मल जनरेशन। तो जितने ये फ्री इलेक्ट्रॉन्स होंगे थर्मल जनरेशन की वजह से, उतने ही फ्री होल्स भी होंगे। तो ये दो चीज अपने आप को बैलेंस कर लेते हैं, और ये बैलेंस होता है इस प्रोटॉन से, तो ओवरऑल नेट चार्ज 0 ही रहना है उसका। ओके so this is the same concept in a different way applies for the p-type semiconductor. So in p-type semiconductor we want to increase the, okay, it is now 13:49. Okay, so one more minute is left. So p-type semiconductor से हम अपने next class में discussion start करेंगे. After that we will see the concept of majority and minority charge carrier, and then we will start our diode. So please एक बार इसको revise कर लेना, ठीक है। बेसिक कंसेप्ट है, बहुत इजी है, बट भूल जाते हैं कई बार, ठीक है। तो ये जरूरी है जब हम डिप्लीशन रीजन क्यों बना, क्या उसका इफेक्ट होगा, इस सब चीजों के लिए। सो प्लीज डू रिवाइज दिस कॉन्सेप्ट, प्लीज वॉच द वीडियो ऑलरेडी अवेलेबल ऑन द नेट, उसमें प्री रिक्विसाइट भी दे रखा है। एंड इन द नेक्स्ट क्लास वी विल स्टार्ट विद पी टाइप सेमीकंडक्टर, फॉलोड बाय some 2 or 3 more concepts, then we will jump to our actual syllabus. Okay, have a nice day.
सर
Thank you, sir.
Thank you, sir. Thank you, sir.
सर
Thank you, sir.
हाँ पूछो
हाँ।
क्या?
Thank you, sir.
सर आई वांट टू आस्क दैट
हाँ
लाइक
पूछो।
जो वेबसाइट पे वो फॉर्म है, तो वो प्रैक्टिकल जो लेते हैं हमारे से, वो कहते हैं वो भरना है, लाइक वो भरे हैं ना?
नहीं भर दो जो सर आपके टीचर कह रहे, बिल्कुल लैब ट्यूट टीचर जो भी आपको कहता है वो आपको मानना है।
ओके सर। और सर इसकी जो ये रिकॉर्डिंग है, ये कहाँ अवेलेबल होगी?
ये मैं भी डाल देता हूँ, एक्चुअली बहुत उसमें 8-10 ग्रुप है, तो मैं एक अलग लिंक बना के स्पेशली फॉर एमईए ग्रुप वो मैं भी डालता हूँ, ठीक है। आज मैं कोशिश करूंगा आज कंप्लीट
तो
करने।
कहाँ डालोगे मतलब ये वाला?
मैं एलएमएस पे डालूंगा वीडियो लेक्चर रिकॉर्डिंग लिंक फॉर एमईई ग्रुप ऐसे करके।
ओके सर।
उसको आप क्लिक करोगे तो आपको वो फोल्डर पे रिडायरेक्ट कर देगा।
ओके सर, थैंक यू सर।
ओके
Thank you, sir.
ओके, हैव अ नाइस डे।
Same to you, sir.